continue on assessment of progress of corrosion quickly, but we will not go into details of the physics and the chemistry of it. So, one of the most popular method is called linear polarization resistance method, right. Just quickly, without going into much of the electrochemistry and physics behind it. Basically, I have I think I will go to the diagram straight away. If you look at it, yeah, this diagram will give you something, some idea. So, if you connect or if you pass current from outside through the reinforcement, supposing I have a source which can pass current through this. In other words, the corroding electrode or corroding rebar, its potential can change. I can increase the potential by a very small amount, I am talking of the order of millivolts. So, if I change this potential, what happens is when I am changing this potential, I find there is a shift in the potential of this rebar, from its initial stage. You recall we had half cell potential measurement where we connected, this is all moist, the connection is through this concrete, right. Now, this potential now gets shifted because you have applied current from outside, the measured potential will get shifted, and this shift is proportional to the existing corrosion current density. What we call it, rate of corrosion is measured in terms of corrosion current density, because it is an electrochemical process. So, you talk in terms of microamperes, milliamperes per meter square of the surface area of the reinforcement bar, right. So, that is corrosion current density and it is proportional to the corrosion current density. Now, from Faraday's law, we know that to deposit 1 gram equivalent of the electrolyte, you need 96500 coulomb, approximately 96500 coulomb, right. So, 96500 equals to I T, I because current is nothing but coulomb per second, right. So, charge per unit time, flow of charge per unit time, that is current. So, I into T. So, 9650 I T is required to deposit 1 gram equivalent, that is deposit molecular weight, gram molecular weight divided by valency divided by number of charges involved in transfer. So, deposit 1 gram equivalent, right. So, this is what we know. So, that is why corrosion current we measure in terms of corrosion. So, if I am looking at amount of electrolyte that will be deposited per unit area of the reinforcement bar, I will be talking in terms of corrosion current density, So, we talk in terms of corrosion current density. One of the ways is to apply current from outside, right, and see the change in the potential which was already there earlier, half cell potential or rest potential you would have measured, and this is this change in potential, So, this change in potential delta V by delta I is some sort of a measure of the corrosion rate. We will see that a little bit. I will not go into the theory, as I said, I will not go into the theory. So, basically, this is the most popular method, as we call it, concrete linear polarization method, one of the most popular, but not very accurate. I will not say it is very accurate. Indirect methods are not very good till date, there are other issues involved. There are several issues actually involved there. So, concrete also is high resistance. So, actually if you look at the equivalent circuit, you will have concrete resistance, then the reinforcement bar whose resistance is generally neglected because it is conducting compared to concrete, and then you have applied some current here, right, some current ampere current you have applied, actually some current you have applied here, right. So, you have applied some current through some DC source, you would have applied current through some DC source. So, there is a current passing through this is a concrete resistance and this is connected here. Now, polarization resistance is the resistance offered at the interface, because at the interface you have a capacitor. Simplest circuit would be a capacitor, because there are two material and a resistor. So, this one will have something of this kind. Why capacitor? There is an interface, two material, dielectric. So, it can store charges at the interface. So, there is a equivalent capacitor. This is the simplest circuit, one can make more complicated. In fact, in reality to model it you need to have more component in the circuit, but simplest is that you have a capacitor, simplest Randall circuit as it is called. So, you have a capacitor at the interface, but it also offers resistance when you try to pass current through it, and this resistance offer is called polarization resistance, and it can be shown that polarization resistance is a function of the corrosion rate actually which is occurring into the steel bar, right, because the state of corrosion is also dependent upon what is called whether it is in passive state, already there is some slow rate. So, there is a coating on top of the rebar which is not allowing current to progress fast, or if it is allowing active state. So, therefore, this polarization resistance measurement is based on this kind of principle, but concrete's resistance is very high. So, the resistance that I was showing from the concrete surface to this is very high. So, this has to be eliminated, because polarization resistance is only at the interface. Polarization resistance is only at the interface, So, this is what I am saying, there is a capacitor and there is another resistance. So, equivalent resistance of this part is polarization resistance. So, but when I am passing a current and measuring current and the potential changes, that will also be involving this resistance. It is a high resistive media. So, IR drop across this has to be eliminated. This is done either electronically or theoretically also one can do. Plus the way you pass the current, for example, if you look at it, you pass the current through this. Now, if you pass the current, its distribution is not uniform. It will not be something like this, direct vertical. It will get spreaded. So, how much area through which is getting polarized, or where your current is going, applied current is going, that is again uncertain. So, these are the issues, but this has been taken care of by using what is called a guard ring, provide another ring, sort of a annular electrode there through which same current is passed, such that the potential difference along this direction is minimal. So, you want to try to keep it one dimensional flow. So, etc. So, there are some assumptions. So, these are called polarization curves, and you can do it two way using a potentiostat which will measure the which will actually go on steps of delta V change, and at every step of delta V will be constant and corresponding current it will measure. Or if it is dynamic, that is also in the same manner, it goes to a given potential, what is the current. The other way is galvanostatic, that means you increase the current in steps, measure the potential, right. Both are being used actually. Okay, there are other issues involved, I think I will not go into this. So, this is basically polarization LPR method, right. So, one can actually this is how the concrete beam, for example, in a concrete beam this is how the setup would be. This is your reference electrode, this is called auxiliary electrode, to where you are passing the current from a source, then there is a switch here, right. So, constant current sources are there, right. There is through the resistor you can control the current, etc., and this is the circuit. So, there is a voltmeter here which measures the reference potential changes. One can eliminate out this IR drop, some ways are there algebraically as is shown here, but I think I will not go into that. So, modern instrument can do that. Modern instrument will give you how much is a, and from that you can also find out the resistivity of concrete, because you find out IR drop. If you know the R I, not exactly resistivity, but some relative measure of the resistivity you can find out, because you do not know the area, do not know there is some confusion related to area, uncertainties are there related to area, but relative resistance you can find out. For same current, one concrete shows higher IR drop, which means its resistance is more, another which shows less IR drop. So, relative resistivity also you can find out. I think I will not look into this in details, the how you to eliminate IR. Now, this is the guard ring I was talking about. In a guard ring, you have two electrodes through which you pass current. This is one electrode which is annular ring. In plan, it will look like a ring, and there is another ring, right. So, this is the strip, this is outer. These two are at the same potential, so that the flow is restricted within this area. The flow of current is restricted. So, this is how one takes care of, and this is the reference electrode whose potential change you will be measuring. So, you pass current through this and also through this in order to, these are called guard ring, and this is either called auxiliary electrode or counter electrode. They are called auxiliary electrode or counter electrode. So, commercial equipments are available on this line. For example, this is one of those, Repicor. But again, reliability of these measurements, true corrosion rate what it is, it's rather relative. You can possibly say at a given place the corrosion rate is higher, then another place it is lower. Absolute value validities in the laboratory one can validate them, but actual site validation is not very easy, but people do measure. So, this is the instrument looks like this, Repicor is one of them. There are several such instruments available based on different principles, LPR, then there are other you send a pulse and things like that. So, this is how it looks like, it has got a guard ring, same circuit that I was talking about. All right. So, I do not think I will go into the electrochemistry of this at all. Stern-Gerry's equation is what is used to find out corrosion current density. Just let me write out what is Stern-Gerry's equation. If this is the potential applied current versus change in the reference potential, you can change the direction of the current, it will be like that. So, slope here delta V over delta I is a slope which is called polarization resistance RP. Slope of this one is called RP, RP. This RP is related to corrosion current density as B divided by RP, provided you take the area, in a given area, etc., etc. So, what is B? B is called Stern-Gerry's constant, after the name of the people who gave this, Stern-Gerry's constant, and it can be found out again. It depends upon various factors, and these are related to something called Taffel's constant. Again, I am not going into this. So, Stern-Gerry's equation is I core is equals to B over RP, and B is given as beta A beta C divided by 2.3 beta A plus beta C. These are called beta A beta C's are called anodic and cathodic Taffel's constant. I do not think I will go into that electrochemistry, but instruments are available, that is what I want to tell you. There are some instruments of the kind of electrochemical noise. Commercial equipments I have not seen one. Similarly, AC impedance spectroscopy, but this is not yet gone to the field, not yet to go to the field. It is almost similar to our similar to linear LPR instrument. Only thing you do is now you pass alternating current rather than direct current at different frequencies. Now, the capacitance, I said that equivalent circuit was something like this, simple equivalent circuit. So, you are saying there is a capacitance, there is a resistance of the concrete, right, resistance of the concrete. So, you send the signal, or this is connected, send the. So, impedance of this one would change with frequency. What is impedance? Resistance is for direct current, only resistance will be there. So, you have, when you have a directional current pass through conductors which offer some resistances, and we know it is related by Ohm's law, and this R is related to resistivity of the metal or material, conductor, concrete, it can be even concrete, length over A, that we know. I am not going further into that. So, there is some resistance of the concrete at the interface there will be some resistance offered by concrete in the interface. Now, interface has got a capacitor. What is a capacitor? It stores the charge. If you pass a direct current through it, it will store the charge. One of the plate will be at higher charge, another will be at lower charge, and no current will finally flow. But if it is alternating current, one time it will be positive, next time it will be negative. So, the alternating current actually flow takes place, or vibration of the electron about their mean position of equilibrium is not disturbed by putting a capacitor. Only thing what happens is it stores some of this energy, and that one derives, and because it stores some of it, that means it offers some kind of a disturbance to the flow path. So, that's basically the reactance of the capacitance. I will not give you the equation of the reactance and all that, you might have done it in somewhere in electrical technology. And when you have combined this reactance and resistance together in a series circuit, parallel circuits, in general you call it impedance. Impedance is disturbances offered to flow of the current, alternating current, by any combination of capacitor, inductor, etc., resistance and so on. So, a capacitance will provide, capacitor will provide reactance and inductance. So, now this the reactance of a capacitor is a function of the frequency. Like we have 50 cycles, but supposing I change the frequency, it is a function of the frequency. So, one state is DC current where there is frequency 0, and you can vary the frequency. So, if you vary the frequency, from there you assuming typical kind of circuits, various kind of circuits for circuit model for your concrete interface, concrete reinforcement bar interface plus the additional concrete, etc., you can actually find out again polarization resistance, because this is polarization resistance. This component is a polarization resistance. So, from this measurement you can find out polarization resistance, but this is not a in situ technique as yet, not very successfully in situ technique, that is what I was talking about, the circuit equivalent circuit, and one can have the impedance of this portion 1 by Rp, this is the polarization resistance, and it is it is imaginary, because we use complex algebra to model this, mathematically model them, because current peak of the current and peak of the voltage, they are not in the, they do not occur same time in case of a capacitors, because it will store then release. In case of resistance it is same, whenever you have a peak of the current, peak of the voltage will be same. In case of capacitor, actually it will store and then release. So, there is a phase difference, what we call there is a phase difference, 90° phase difference, and therefore, complex algebra will show you this is how, this is a j omega stands for the angular frequency twice pi f, and C is the capacitance, equivalent capacitance of the interface. So, you can write it like this, and overall Z1 one can then write. I am not interested in writing, but I am just. So, you see, if you measure the complete circuit, complete circuit impedance, you can get an expression for complete impedance of the circuit. So, impedance of resistance of the circuit will be Rc plus Rp, because they are in series. So, when you are, it is DC current, 0, omega is equals to 0, omega tends to 0, you get equivalent impedance as this, and when omega tends to infinity, because this is omega tends to infinity means this part will be very large, right, this part will be very large. So, nothing will flow through this, actually everything will flow through, everything like nothing will like is as if this the current everything will flow through this, there is a current short circuit. You can show that when omega is very large, this part is 0, so it is simply Rp. Omega is Rc is simply Rp. If I divide by Rp, I get 1 by Rp. No. So, omega is infinity. Overall, from the circuit, it will turn out to be Rc. It will turn out to be Rc actually. You can calculate the equivalent circuit and use omega being very large. So, it will turn out to be Rc. This was for Z1, only this part. So, one can calculate this out. Yeah, this is the formula actually. So, I do not think I will go into the derivation of this. So, one can show that when omega tends to 0, this is Rc plus Rp. when omega tends to infinity, it is RC. So, if you measure it at different frequencies, very high frequencies, equivalent impedance is RC, and very low frequencies or 0, it is RC plus RP. Difference of this gives you RP. This is one of the ways of finding. This is found out through what is called, these are one can derive this. This is actually, there are two diagrams, Nyquist and Bordes diagram. So, from those plots you can actually find out. Typically, this is what is shown in something like this, omega increasing RC, RC plus RP. So, this is nothing but, if you subtract RP, this will be simply this portion will be simply RP, this portion will be simply RP. So, you can find it out, you can find out from this kind of measurements. Okay, this derivation, I think I am not interested in this. One can show that, RP by 2 will be the radius. So, people plot different types of diagrams, and from that actually obtain the polarization resistance, and one can obtain. But this is still till date it is more of a laboratory based technique rather than into the actual site, So, that is what it is. Other way of measuring is simply measure by mass loss. So, what you do from actual structure where it has corroded at a given time, take out a small piece of bar, and if it is laboratory type, then this one has got corroded, just make it to fail, the bar, make it to fail. There is a reinforcement bar which has corroded. You can see it is covered here, so that no corrosion can come from outside, it was corroding from inside. So, once corroded, you might get something like this. This is before corrosion, after corrosion, bar will look like this. You can say this is corroded, right. Then you wash it off and find out the original mass is known to you, you find out the remaining mass, and if you have found out the area here, then you can find out the corrosion current density. So, this can happen for various steel types, you can find out, etc., etc. I think I am not interested, I am just showing this is corroded, this is corroded, highly corroded, something is less corroded. So, this is gravimetric thing you can do in the laboratory to test, but actual site if you are doing, unless you have done it at number of time, you won't be able to know whether what is happening rate, because you got to know it at different times. But at a given time you want to find out, cut a piece of steel bar, clean it with either there are there's basically it is done with two sorts of solution. One is hexamethyl tetraamine or Clark solution, right. So, Clark solution is basically stannous chloride, antimony chloride in acids and so on. So, we know that, and this is hexamethyl tetraamine. So, you dissolve them, first you brush it off, then apply this solution on top of the rebar, all the rust will get dissolved, intact iron will remain as it is. So, you can find out the mass. So, this is prepared by 500 ml hydrochloric acid with 3.5 grams of this. This solution if you apply at the surface, rust get dissolved, still remains as it is. So, what done is one does number of cleaning actually, cleaning time, and then after a certain period of time you find that mass loss is not, change in mass is very little. So, initial mass you find out how much is the mass, 0 mass loss in the beginning, then some with time. So, about it is something of the around 8-10 minutes you have to do that cleaning, keep it in that water. So, that then it goes. So, that is it. People okay, one can compare AC impedance spectroscopy and LPR by the same instrument, this is possible. Gravimetric laboratory you can compare, but actual site doing LPR and then doing gravimetric, then gravimetric you have to do over the years many times to find out the rate. So, that kind of validation has not been really done much. I said this is one of the measurements like RAPIC or measurement I was telling you. So, commercial instruments are very much there, and one can use them. Okay. Now, let's look at magnetic mass probe. It can actually tell you how much is the quantum of rust at any point of time. So, basically these are the probes actually, and you can see that the image that you get, that will tell you how much is the, because modern instruments they can actually bring out using softwares. So, how much is the amount of rust and how much is remaining. So, this is the technique used to find out the quantum of rust, but then this is very costly instrument, not very easy, not very cheap, right. So, things like impulse radar technique, magnetic mass probe, they can give you a lot more information in addition to whatever conventional NDTs are done. So, if you look at corrosion, corrosion actually if you look at it, it would be first you have some visual survey, you will get rust staining. So, if you get rust staining, rust stains, then corrosion is occurring, right, or cracks, spalling, break it and see. Then you can do some chemical test onto the concrete, whether chloride is there, carbonation is there, and you can do some test on the structure itself, NDT, to demarcate those areas which are potentially high risky, because half cell potential or resistivity test will tell you that. Now do some rate testing there, do corrosion rate testing at those locations where you have already found out, demarcated using other techniques. Or even if you can break, even if it is already damaged, cracked, you can break and see how much is the mass loss. At different places you do, there is of course the other statistical aspects and quantification of the total mass loss potential, etc., you can find out. So, this is how it is done. So, basically you can do, if you do a number of case studies which are being reported here, but one thing is found out, most of the cases diagnosis was done and it was found corrosion, and many of them are our own investigation actually. So, what we find is, if you see this table, different types of buildings, right, residential, textile factory, residential, office, etc., and construction is either RCC or load bearing masonry and RCC slab, because many of the old low rise buildings were load bearing masonry with RCC slab on top. And when they came for investigation was taken, because people do not investigate in between. Once they face the problem, when you need extensive repair, then only you come and investigation. So, age at which investigation was done is approximate, age we will say. This varies from 5 years to somewhere you will see 5, that is the minimum, and maximum will be somewhere 50 or so. So, some buildings showed excessive corrosion distress after 5 years and some showed after 50 years. So, but major factor, so you can see the construction year also is noted in your slides, you will find. Obviously, this was done in 1990s or around 2000. So, this is related to the 50 years means 1950 or 48, 1948 of those kind of things. Okay, and their heights were, one of the building was 28 story, 21, and others were less, single 2 story, even single story. What is major one finds, what is the cause is essentially one would find that cover depths were very low at many places, particularly which has survived only 5 years. The 5 years, the one which has survived 5 years is number 13. And if you see number 13 here, its cover is this had good cover anyway, cover was good, but many other places the covers were not good, 2 millimeter to 81, 5 to 36 and all. This had cover, but this is other problem, chloride. This is high chloride, relatively much higher chloride than most of them, going up to 0.4 percentage by mass of concrete, 4.4, actually 0.015 or 0.025. Beyond that, risk of corrosion becomes very, very high. Percentage by mass of concrete, not percentage by mass of cement. There are other ways people talk in terms of percentage mass of cement, but then you have to find out what is the cement content. In an old concrete, it is difficult to find out what is the cement content. So, it is much better to express them in percentage of concrete. So, this is one thing was found. Then pH of the concrete soil looked into, some cases pH was low, but this, since this is in northern India, majority of them showed actually chloride coming. Now chloride would have come from the ingredients here, because there is no seashore. So some correlation was obtained. Quality of concrete, ultrasonic pulse velocity, if where pulse velocity is high, approximate year of repair cycle was also higher. That means good quality concrete survived for longer years, good quality concrete. So one thing is, one should actually look into this. And other thing was, cover was a factor. Chloride concentration was more than that caused depassivated in 16 out of 22 cases. The 22 cases, 16 cases chlorides were high, and carbonation was high in 7 out of 22. So one can actually, using this actual data, measure data over large number of years, simple regression would give you something like time of repair as a function of ultrasonic pulse velocity, the strength, the cover depth, right? Strength and cover depth. Some are good cover was there, some are bad. So what one finds is, if your concrete is generally good, first level, you might require longer time, repair cycle will be longer. That is one aspect. The cover is other aspect. Generally good means both in terms of soundness, in terms of ultrasonic pulse velocity, but it should not be contaminated. These are all contaminated ones. These are all contaminated with chloride. Majority 16 out of 22 are contaminated. 16 out of 22 are contaminated. So if it is contaminated, then also good concrete, relatively higher resistance, etc. is better. So concrete quality is a major factor, and contamination should be avoided fully. Steel bars, different types, all had actually cold twisted deformed bars. So major one of the thing was that.